Every day, the world produces about 418 million pounds of aluminum, the backbone metal that supports countless industries. In the United States alone, demand exceeds 11.9 billion pounds each year. Few realize that sustaining this scale of production devours an immense amount of electricity, earning aluminum the nickname solid electricity in the modern metallurgy world. The story of aluminum begins in the Earth's crust, with a reddish-brown ore rich in aluminum oxide, known as bauxite. Awakened by the roar of steel gears, it embarks on a transformative journey. Ground into fine powder, dissolved in hot caustic soda, filtered, crystallized into white alumina, then fired at extreme temperatures and electrolyzed under powerful electric currents. Each stage like a gate to pass through, gradually revealing its primal metallic shine. So what turns this humble red rock into a gleaming silver metal? Let's uncover each step, where human skill and technology intertwine to breathe new life into an ancient element. Unlike many metals that rely entirely on finite natural reserves, aluminum holds a secret weapon. It can be recycled almost endlessly without losing quality. This advantage is especially evident in the United States, where the aluminum industry has refined its recycling technology to the point that nearly 75% of all aluminum ever produced in the country is still in use today. While China leads global production thanks to abundant resources and lower costs, the U.S. stands out with its prowess in refining and recycling technologies, as well as its ability to produce high-grade aluminum for aerospace, defense, and electric vehicles. Put the two economies on the scales. China may dominate the market through sheer volume, but the U.S. controls the top tier of the value chain, where added value and technical standards define true advantage. The question is, who truly holds the power in an era where aluminum has become a strategic material for nearly every future-oriented industry? From a long-term strategic perspective, aluminum surpasses many finite resources thanks to its infinite recyclability, reducing dependence on mining and minimizing environmental impact. With demand for aluminum soaring in clean energy projects, the United States has a real opportunity to turn its technological edge into a ticket for global leadership. It all begins in bauxite mines, reddish-brown rock rich in aluminum oxide, the raw ingredient behind the gleaming metal so essential to aerospace, construction, and electronics. Unlike gold or silver, bauxite is abundant in tropical and subtropical regions, especially in Australia, Brazil, and Guinea, the world's vast stockpiles for aluminum production. Beneath what seems like ordinary soil lies a valuable resource, waiting to be unlocked by heavy machinery and advanced mining technology. Accessing this ore starts with removing the overburden, a task far from simple, as most bauxite lies buried under about 16 feet of earth. Geologists survey the terrain, drill deep holes into the ground, then charge them with a mixture of ammonium nitrate and liquid fuel. A single blast can unleash enough force to topple a 10-story building, breaking apart stubborn rock and earth to expose the ore below. Large mines may consume 770 to 990 tons of ammonium nitrate per month, generating a series of blasts across areas spanning dozens of acres. As the echo fades, massive excavators move in, scooping up bauxite blocks weighing several tons and loading them onto ultra-heavy trucks. In a single mining cycle, crews can clear about 5 acres of land, yielding between 55,000 and 110,000 tons of ore. It's a continuous rhythm, from breaking ground to hauling loads, like a giant machine working around the clock to bring bauxite out from the earth. Once stockpiled, bauxite is swiftly transferred onto conveyor belts or funneled into deep hoppers, sliding straight into the holds of bulk carriers. At coastal mines, conveyor systems can stretch for dozens of miles, running non-stop and sending a steady river of crimson ore out to the port. Massive cargo vessels, each longer than 3 football fields, are capable of carrying more than 220,000 tons of ore in a single voyage. Fully loaded, they slip quietly from the docks, joining international shipping lanes that link bauxite-rich regions to refineries across multiple continents. From the port, bauxite is fed directly into the processing plant. Traveling along extended conveyor lines, the ore moves steadily toward massive rotating drums filled with tons of steel balls. As the drums turn, thousands of these balls tumble and collide, grinding the ore into a fine powder with a texture almost like flour. This powder is mixed with a strong, caustic soda solution and heated. Under these conditions, the valuable aluminum oxide dissolves, while impurities such as clay, iron, and silica are separated into a dense, rust-colored residue known as red mud. The aluminum oxide-rich solution is then filtered and cooled, allowing tiny white crystals to form. Once dried, these crystals become alumina, a fine snow-white powder resembling beach sand, refined to high purity and ready for the next stage of aluminum production. After refining, the aluminum oxide is dissolved in molten cryolite and fed into massive electrolytic cells operating at temperatures between 1742 degrees Fahrenheit and 1832 degrees Fahrenheit. An immense direct current, on a plant-wide scale, 900 megawatts for the entire line, flows through the cells, breaking the bond between aluminum and oxygen. Molten aluminum settles at the bottom, while the oxygen reacts with carbon anodes to form CO2. These carbon blocks both conduct electricity and participate in the reaction, but gradually wear down and must be replaced periodically. While the electrolytic cells run continuously, workers in reflective protective gear collect molten aluminum samples at nearly 1,832 degrees Fahrenheit, 1,000 Fahrenheit. The samples are cooled and tested to ensure they meet all specifications before casting. This process consumes between 10,000 and 15,000 kilowatt hours of electricity for every ton of aluminum, meaning a large smelter can draw as much power as a mid-sized city. Since electricity accounts for up to 1/3 of production costs, aluminum plants are typically built near inexpensive, stable power sources, earning the metal its nickname, solid electricity. This cost is measured not only in the utility bill, but also in the CO2 emissions generated and the strain placed on the national power grid. That's why the modern aluminum industry, especially in the United States, is shifting strongly toward recycling. From beverage cans, window frames, and car bodies to retired aircraft components, scrap aluminum is collected and sorted, separated from steel, plastic, and glass. At the recycling plant, the material is shredded, cleaned, and melted at about 1220 degrees Fahrenheit, far lower than the temperature required to produce aluminum from bauxite, to remove impurities. The purified molten aluminum is poured into molds, forming ingots or sheets ready to begin a new product life cycle. The entire process uses only about 5% of the energy, generates virtually no red mud, and significantly reduces emissions, making recycling both an economical and environmentally friendly solution. Molten aluminum from the electrolytic cells or recycling furnaces is transferred into massive heat-resistant ladles, then poured into inclined troughs or casting molds. Throughout this stage, the temperature is maintained at around 1292 degrees Fahrenheit, 700 degrees Celsius, to ensure a smooth, uninterrupted flow of metal without premature solidification. The molds, made from heat-resistant steel or cast iron, vary in size depending on the product, from standard ingots weighing 48 to 55 pounds to long billets weighing several tons. As the aluminum cools, a thin gray film forms on the surface, a natural layer of aluminum oxide created by contact with air. This will be removed or treated in later processing stages. Water-cooled and air-blown systems surround the molds, allowing the metal to solidify quickly yet evenly, minimizing cracking. Once solidified, the ingots or billets are removed, checked for dimensions, weight, and surface quality before being packaged or sent directly to rolling, extrusion, or final product manufacturing plants. Once the ingots or billets are removed from their molds, they are moved to the inspection area. Here, technicians measure dimensions, weigh each piece, and examine the surface for cracks, gas porosity, or deformation. Some samples are cut into smaller sections for chemical analysis, ensuring that the aluminum purity and alloy composition meet strict standards. Products that pass inspection are stamped with identification marks, including batch codes, production dates, and plan information before being placed on pallets or secured in specialized steel racks. Both standard ingots and multi-ton billets are wrapped or firmly fixed to prevent damage during transport. From here, the shipments leave the plant by truck, rail, or sea, bound for rolling mills, extrusion facilities, or component manufacturers worldwide. This final step closes the journey of transforming bauxite ore into aluminum, ready to serve thousands of industries. In the aluminum foil industry, the journey continues. Immediately after leaving the smelting line, massive solid billets, several meters long and weighing multiple tons, are sent directly to the rolling mill, where the process of turning them into aluminum foil begins. At the hot rolling mill, massive solid billets of aluminum, about 10 to 15 feet long and weighing thousands of pounds, are loaded into giant furnaces maintained between 930 and 1020 degrees Fahrenheit. This intense heat softens the metal, increasing its malleability and reducing the risk of cracking during processing. Once the proper temperature is reached, the billets pass through a series of large-diameter steel rollers. Under high pressure and speed, each pass compresses and elongates the aluminum, reducing its thickness from over 4 inches to just a few tenths of an inch, while producing a smooth, uniform surface. Between passes, high-pressure water jets remove oxide layers and aluminum fines, ensuring the surface stays bright, smooth, and free of impurities. At the end of this stage, the large aluminum sheets are either wound into semi-finished coils or cut into flat plates, ready for the cold rolling process that will achieve the final thinness characteristic of aluminum foil. Have you ever wondered why aluminum foil has one side that's shiny like a mirror and another that's duller and matte? The answer lies in the very last stage of cold rolling. After multiple passes through huge steel rollers to thin the aluminum, the final pass is done with 2 sheets stacked together to save time and boost output. The outer sides, pressed directly against the rollers, are smoothed and polished, giving them that signature shine. The inner sides, touching only aluminum, retain a slight texture and appear matte. Interestingly, this difference has almost no effect on the foil's strength, durability, or heat conductivity, but it does create different uses. The shiny side reflects heat more effectively, keeping things warm longer, while the matte side reduces glare and grips food better when wrapping. Next time you use aluminum foil, take a closer look. You might just change which side you choose. Before packaging, each coil or sheet of aluminum passes through a network of laser sensors and optical cameras that measure thickness down to thousandths of a millimeter, while scanning for scratches, pinholes, or surface distortion. Random samples are also taken to test tensile strength, ductility, and resistance to moisture and heat under extreme conditions. Once the aluminum sheets meet quality standards, they are cut into panels or coils according to the customer's specifications or the requirements of end-use applications. For boxed formats, sheets are fed into an automated packing line, which encloses them securely to protect against dust and scratches during transport. This automated process ensures speed, precision, and consistent quality. For coil production, operators feed the aluminum sheets into a winding machine, where they are tightly rolled into large coils ready for shipping or further use. Throughout the process, workers monitor coil tension to prevent wrinkles and maintain even winding. The coils are produced with precise tension control, making them easy to store without damaging the aluminum surface. While the winding machine performs most of the work, operators adjust winding speed and roller pressure to prevent deformation. Finally, the finished coils are packaged and moved to storage or prepared for distribution, ready to serve industrial and consumer applications worldwide. Aluminum doesn't end its journey in the form of thin foil for packaging or food service. In the worlds of engineering and construction, it takes on another path: aluminum extrusion. Here, cylindrical billets are heated to about 842 to 932 degrees Fahrenheit to make them malleable while retaining structural strength. Under the immense force of a hydraulic press, the billet is pushed through a hardened steel die, precisely shaped to the desired profile. As it emerges, the aluminum takes the form of long, continuous bars, tubes, or intricate profiles, perfectly uniform from end to end. These extrusions are rapidly cooled by air fans or water sprays, then passed through straightening equipment and cut to exact lengths. The result is a range of lightweight, durable, and highly accurate components, ready to serve in everything from window frames and glass facades to machinery parts and modern vehicle structures. Thank you for joining this journey into a metal that feels familiar, yet is rarely seen up close. Aluminum is more than just foil, window frames, or airplane skins. It's a testament to how human ingenuity blends metallurgical knowledge, mechanical engineering, and industrial precision to transform raw ore into a material that shapes the modern world. If this video has made you appreciate the quiet presence of aluminum in your life, don't forget to like and subscribe. Because behind every material that seems ordinary lies a remarkable journey, where technology, human skill, and nature intersect in ways you may never have imagined.